I'd like to talk now about file permissions. We'll have a look at the initial permissions assigned to a file when it's created. We'll see how those are limited by a setting known as the umask, and we'll see how to change file permissions. Now, when a file is created, either with the open system call or possibly with create, the initial mode, the initial permissions, are set explicitly. Here I've specified them as an octal constant. By the way, there are some symbolic constants that make this a little easier to work with. I'll show you those shortly. The standard I/O library routine, fopen, gives you less choice. The initial permissions are implicitly set to 666. However, it's not quite as simple as that, because every process carries around with it a value called the umask. Now, you may be familiar with getting and setting the umask using the umask command on the command line. Now, the umask is a bit mask of permissions not to be assigned. That's a little confusing, so let me give you a worked example. A typical value for the umask is 022. If we write that down in binary, we would get 000, 010, 010, as I've shown. If we take the ones complement of that, we get 111, 101, 101. So there we're just flipping the zeros to ones and the ones to zeros. Now suppose we create a file and we request a mode of 666. Which in binary is 110, 110, 110. What happens is that requested mode gets bitwise ANDed with the ones complement of the umask to actually give the mode that will be assigned to the file. In this case, it will be 644. Some people like to say that the umask is subtracted from the requested file permissions, which isn't strictly true, but it's a cheap and cheerful way of thinking about it if you're frightened away by the idea of a ones complement and a bitwise AND. You can get and set the umask with the umask system call, which is pretty straightforward. Be aware that the umask is a property of the process. It will be inherited by any child processes you create, but if you change it in one process, it doesn't propagate sideways, so to speak, into other existing processes. Also, be clear that the umask only plays its part at the point at which a file is created. Changing it will not retrospectively affect the permissions attached to existing files. You can change a file's permissions subsequently by calling chmod, which is short for change mode. The call is pretty straightforward. You can only change permissions on files that you own, unless, of course, you're root, in which case you can do pretty much anything. Again, I've expressed the permissions as an octal constant here. Obviously, the chmod command is essentially just a wrapper around this system call. Rather than using these octal constants, you may prefer to use some symbolic constants that are defined for you. Here they are, corresponding to the different permission bits. They don't have very pronounceable names, so each of these corresponds to one bit, and they are intended to be bitwise ORed together to give you the combination of permissions that you want, as I've suggested in this example here. Frankly, I don't find these terribly easy to interpret and actually prefer to use a simple octal constant. After all, in practice, there aren't really that many combinations and values in use. I have a very simple program for you here that just demonstrates some of the system calls we've been talking about. We begin here by setting the umask to 0. That effectively turns it off. It will have no effect. Then we create a file called f1 with the mode 755. Then we create f2 again with the mode 755, but this time we've set the umask to 7. and you'll see the effect that that has when we run the program in a moment. Finally, we create a file called F3 with no permissions at all initially, but then we use chmod to set some permissions on the file, and here I'm using a couple of those symbolic constants that we saw to set the permissions. These two represent the read and write permissions for the file's owner. And finally, we use the system library routine, which invokes a shell and passes it a command line, this command line here. In this case, I need a shell to see the command line because I need it to expand that question mark wildcard. Now, there are other ways I could have done this, to be sure, but I thought it would be interesting for you to see the system library routine. So let's try running this. Make some files, it's called. And here we see the output from the ls that was executed at the end of the program. The permissions on F1, this is the 755 permissions, which have not been affected by the umask. But interestingly, if you look at the permissions on F2, these bottom three permissions have been suppressed by the umask value. And then finally, the permissions on F3, we just have read and write permissions for the file's owner, as we expect.